see some background topics like a diode and the transistors for today's class. And then from next class, we will go to our actual syllabus and the topics of our syllabus. But today, first thing is diode. As you already studied the diode, and I think you are very sorry, and very still can remember the diodes. But we need some of the basic stuffs. Let's say here, right? So we already know that this diode is made out of two junctions, right? A P and N, right? P and junction, and P inside the P, right? P-type material. Both are silicon, right? Or germanium or whatever. Most of the times we'll consider that this everything, all kinds of devices are made out of silicon. Right? This is the most common component. So we are not considering the other materials, and there are so many other materials, but we'll mainly considering this is both silicon and monolithic transistors. And monolithic, we mean actually the both sides are made out of silicon. Right? There are some transistors that are made out of. Oh, can you see the board? Is it all right? Can you see my?
Yes, sir. Yes, sir.
Yes, sir.
Oh, from my side, is maybe something is wrong. I can see the mirror image of. Okay, we'll fix it later. Right. তোমরা দেখতে পেলেই better. Right? আমি তো কম্পিউটারের দিকে তাকাচ্ছি না, কিন্তু আমার কম্পিউটারের স্ক্রিনে এটা মিরর ইমেজ আসছে বোধহয়, এটা ফিক্স করতে হবে নেক্সট টাইম। We'll see that. Anyway, so the both sides are silicon, but in some cases, like there are so many advanced materials, advanced transistors, very fast, more efficient transistors. So in that cases, those this P and N, these two sides are made out of different kinds of materials. Like in here, let's say in this side is gallium, and this side is this is gallium and arsenic. Right? There are let's say this is a P-type and this is N-type, but the material, the base material is different. Right? Or sometimes this is indium, aluminum, gallium arsenide also. Aluminum, gallium arsenide. And there are so many different materials are also there, but we don't care about that. That is for advanced courses. But remember, those are very efficient transistors. Right? Compared to silicon transistors, they are maybe 10 to 100 times faster. And some of those transistors are already in your cell phone. Those who have expensive cell phone, smartphone, right? The expensive one actually using those high performance transistors, right, made out of
So in
compound.
the chip, we also use silicon transistors, or we used other transistors.
Mostly silicon. The cheapest one, silicon is cheaper, right? Silicon is a sand, right? We can get the silicon from sand, right? The Bali থেকে আসে, right? The silicon is cheaper compared to the other material, and that's why the most of the ICs are made out of silicon. The base is silicon. But yeah, advanced computer, like normally the communication devices, right? Especially the communication, right? Your smartphone is mostly one of the smart device. Smart is most efficient communication device. So in case of communication, high speed communication device, we need to process the information more faster than the normal computing operating computer operation. And so those in order to fabricate those high efficient IC, we need those compound material. And as I mentioned before, again, aluminum, gallium arsenide, or gallium arsenide, or indium, pentium. Those are the materials. Those are expensive, right? But the electron and the hole and the carriers can move more faster through those kinds of materials, through those compound materials. we call compound, because there are this the divide this one let's say this one P or one N type area is made out of three different materials, right? For example, aluminum gallium arsenide, right? So you can use aluminum gallium arsenide in this side, and also you can use aluminum gallium arsenide in this side instead of silicon, right? But that actually this that three different uh, compounds, three different materials actually forming one compound, but acts like a single material. Right? Those aluminum, right? This is aluminum, gallium, and arsenide. This actually working just like in one, only aluminum or silicon, right? One of the atom from here will be acting just like the one of the atom from here or one of the atom from here. So, but in this one is expensive, but interesting is all kinds of carriers, especially the electrons, moves more faster in here in this material than silicon or germanium. So since the carrier is moving more faster, so then it can process the information more faster, and so especially we need for communication device, all kinds of communication equipments. That's why those you are using more expensive, using the same kinds of cell phone, right? And some of the cell phone, like my one, right? This cell phone is just only 5,000 taka, right? But some of you are using like iPhone and is like more than lakh, right? Or 70, 80,000 taka. So that's why is that doing the same job? Because yeah, normally I do not use internet for my telephone. It's I'm using only for making a call or receiving a call. But some of you are using maybe in the class, right? By using this smartphone. Yeah, you need maybe for that. If I use this one for this class, and for yeah, some teachers also sometimes using those the internet package by using his or her cell phone and conducting class. So in that case, we must need a very high efficient, right? Otherwise, it will be slower. And if I use this one, maybe I cannot talk, right? Or maybe it's done so many buffering and will be slower, and I cannot hear me, I cannot see, right? So why is this expensive than the other one? Doing the same job, because those the ICs are made out of those compound material. Right? So that is expensive, and that's this informations are processing faster and transmitting faster. Right? But we are not going to study that, because that is actually higher level. Normally, senior level student, those who are studying those integrated circuit design courses, they are learning. So what are the special properties of these kinds of materials? Some of those materials are very interesting. Like if you in here consider here how you already studied this in here. In here, silicon. What kind of carriers are in here? Let's say in P-type, there are mostly positive ions, and but there are some negative ions also, right? Let's say here, right? There are few. Let's say there are 9 positives and maybe 4 negative. Right? And in this case, in the other side, in N-type material, maybe there are more holes, than electrons. And let's say there are few electrons and mostly holes, right? So can you see those green color and blue color?
Yes, sir.
Okay, good. But in my screen, it looks like all black. Okay. Anyway, so if this you see in here, so now what happened when we the basic working principle of the diode. So what happens when we apply some voltage, right? When we apply in here, if you apply some positive voltage here, a positive. When you apply the positive voltage in the positive side in here, right, positive terminal, the P terminal, and negative in the negative N terminal, then what will happen? Some of those, what will happen? Anybody tell me what happened to the electron here? Oh no, oh no, I did a mistake, right? Why did not you say me? I did not do mistake here in diagram. There will be hole here. Hole. And this is more negative here. Negative. And more electrons. This is electrons, electron. Right? More electron, and let's say this 9 electron and or 4 holes. At 1, 2, 3, 4 holes, and 1, 2, 3, 4, 5, 6, 7, 9 electrons. But in this side, there are 9 holes and 4 electrons. Right? This is just an example. So that means in N side, there are more electrons, free electrons, and in P side there are more free holes. Right? Those are free, so they will be they are ready to move from one side to the other side. Right? If we apply some electromotive force, right? So where the electromotive force coming from? From the voltage. And if we apply some voltage here and here, and there is a positive, and the positive terminal connected to P side and negative terminal connected to N side, then what will happen? Because of this, because this voltage will positive voltage will apply some electromotive force on these free holes, and this negative one, this one also right, will apply some force on the electrons. So the electrons will start, right? They will feel some external force, and then they will try to move to the other direction. Right? It depends on what kind of force. It's a repulsive or is an attractive force. Right? Normally, when you apply in here negative with a negative N terminal, so then this is negative and this is negative, so there will be some repulsive force. Right? So because of the repulsive force, these electrons will try to move away. Right? From here, this is negative, right? So they will be pushing each other from far away. It will move from the same point. Right? If you consider these two things, right? Two things, both are the same polarity, right? So they will not attract. There will be a repulsive force. They will try to move away, right? Just like this. And the same thing happened from this side also. The positive here, positive voltage applied to the P type, and so what happened to these holes, free holes? Right? The same thing happened in this side also. The free holes will try to move away from here, and not in this direction, but this direction is holes already there. They will not come in this way. They will try to move the other way, right? And there is electron here, right? The free electrons in this right side and free holes in the left side. So they will attract each other. This, right? If you consider any one set, right? We can consider, let's say, this one and this one. Right? They will attract each other. Right? So they will try to cross. So these holes will try to cross this boundary line. Right? This is a black. This is a virtual. Right? This is not a real. This is a virtually boundary line, and so this one will try to cross this way, right side, and these electrons will try to cross this left side. So, and somewhere in the middle, they will join each other and will be neutralized. Right? They'll be neutralized. So now look at here, when the electrons and holes are moving actually from one side to the other side, but there are some other other carriers are also there. Let's say in here there are more holes, but electrons are there. and in here electrons, but holes are there. So when they are going to move, so they will collide with those things also. There will be collision with the other atoms, right, in here or anywhere, right? Because there are so many different kinds of other kinds of uh, carriers are there also. So there will be collision. But in here, it's interesting. There are some types of there are advanced materials are used to design some special types of transistors. Right? In some transistors, there is no there will be no collision. Right? If there is no collision, then those carriers can move more faster. Right? So in most of the cases, actually, in most of the transistors, there are collisions. And even we will study in next few classes, the MOSFET. I told you this is the most popular components. But still, in MOSFET, there are collisions as well. There will be some collisions too. But in some transistors, like we don't need to remember, is no, it's EMT. High electron mobility transistor. Right? You don't need to remember. Just for example, right? I'm just giving you some flavor. Right? HEMT. Right? High electron mobility transistors. In this kind of transistors, right? You cannot make these by using the silicon. Right? There is no way you can make a high electron mobility transistor by using silicon or germanium or any kinds of like a monolithic. I said monolithic. There's a single material, right? The silicon or germanium, just or if you want to use aluminum or gallium in a different, just a one by one. If you use this one, or this one, or right, or you cannot make this kind of transistors by using individual material. If you want to make high electron mobility transistors, you have to use this compound. It's a compound, right? It's made out of three different material and making one material. So that's why this is expensive. And in this kind of transistors, right, this is interesting. Or you can make a diode also. The ACM instead of transistor, you can make high electron mobility diode also. But in that case, and there will be no collision. That's interesting. So if there is no collision, so that's those electrons or holes.
So why there will be no collision? In HEMT, there is no free holes.
Yeah, no, here, no, when we make this kind of the compound
They
material,
become neutralized.
no, when we make this compound materials, the hole will be hole means there will be a vacuum place is formed inside, right? So in the when there is a vacuum, and if we want, let's say, yeah, I can just make a rough diagram. Let's say when we mix this one and when we make a compound material, let's say this is a one piece of this one, and by maintaining some ratio, right? You cannot make the same amount of aluminum, gallium, and let's say you have to maintain some ratio. Let's say if we consider this one as a 3 and this one, no, this one let's say 0.3, this one 0.5, and then this one 0.2, right? Like this way, you can actually make altogether it must be one, right? Because you have to make it 1, 0.3, 0.5, and 0.2 is making 1. So it will be acting just like a silicon, just right? There is a 1 actually. Nothing means 1 atom. So in here also will be 1 atom. So when we make by changing this ratio, in right, we can make those compound in such a way that, that there will be some vacuum. Right? Let's say here, let's say a channel, a vacuum place will be formed. Understand? So if there is a vacuum, let's say, just for example, if there is a vacuum here, and if you want, and if you somehow, if you bring some of those electrons from here and put it in here, right? maybe 1 or 2 electrons, you bring it here by using some electric field. And if you apply some field in here, let's say positive voltage here, so then what happened? Some of the electrons will be coming from here and will be sitting inside this vacuum. And now apply another voltage in this side, right? In this side, if you apply another voltage in here, let's say in this way, right? Now what will happen? This electron, now this is a negative and this is a positive. So what happened? This electron will be attracted by this hole, and these electrons will be forced by these electrons, right, from here. So this electron starts to move this way. But in here, because of the vacuum, the electron move more faster. Understand?
Yes, sir.
The technique. So, but there is some techniques, right? By using some techniques, so there will be a vacuum will be generating. Right? Automatic, there will be no automatic things, right? You have to maintain some ratio and apply some specific amount of voltage, and then the channel will be formed, and that will be interesting. Right? But you cannot make by using this one. You cannot make, because in here you cannot maintain this kind of ratio. Understand? These things cannot be maintained in one. When you have only one kind of material, you cannot maintain those ratios. Right?
So the vacuum being formed, it depends on the ratio of the.
No. It depends on the band diagrams. Do you remember the band diagram you studied in physics? Let's say the conduction band. What's it? What's called? Let's say here is a conduction band EC, and valency band here, let's say EV, and then in somewhere in here is a Fermi level EF. Have you studied like that? Things like that in physics? Cannot remember?
Sir,
Familiar like this.
Yeah, because you see, look at here. Every material have a different energy level. This is actually this E. I'm talking about bands though, but actually I'm showing here is E. E means actually energy. Energy means actually the energy of the electrons or hole. Free holes and electrons have a specific amount of energy. So in here, let's say in silicon, so there is free electrons. You see here, and there's free electrons in this side. So these electrons have a specific amount of energy. And when it's a conduction band means this, when electron sitting here, when electron sitting on top of this is a Fermi level, right? This is not in the middle, right? We can change it by using by applying some external heat or some other external influence. Let's say the one electron sitting here or here, right? These electrons are free to move because they have enough energy. Right? They have enough energy to move around. But if you consider the electrons here in this point, so that means this electron has a very low amount of energy. And these electrons actually is prefer to sit here instead of moving around. Right? If you consider like a person, like you can consider a person who is let's say very fat and is not so healthy, right? But and always staying home, like things like that, have no enough energy to work or going some work, like this kind of here. But let's say athletics person or a healthy, a young like you, right? So you don't like to stay around, right? You don't like to sit down at home, right? You always try to do something. So that means you are in a conduction band, right? So that means you have enough energy. So you right the electrons or whatever, right? Those are almost free to move away or move around. But these are not, have no enough energy and try to sit close to the zero level. Right? This one, when you go here, there will be no movement in here. But the interesting is, let's say in here have a the electrons or the carrier is living here. But if you apply some heat, then what will happen? When you apply heat, what happened to the electrons or holes? Or you can consider a metal. Let's say for a piece of iron, right? What happened? Let's say the piece of iron, right? And it looks like there is nothing happened. But if you want to apply heat, so what will happen? If we apply heat in the left side here, and after a few seconds or maybe a few minutes, you will feel heat in this side, right?
Yes, sir. So
Yeah.
the electron will move from lower
Yeah.
bound to upper bound.
Yeah. When there was no heat, the electrons in here has no enough energy or was not moving, right? But when you apply heat, here, the electrons will move from the valency band to the conduction band. They will move here, move above this Fermi level. This is the actually you can consider this the reference level, right? When it goes above this, then they are free to move. Right? So when you apply heat, the electrons will get some energy and then it starts to move. But if there is no place to move in this way, right? Then what will they do? If there is no way to move, so that they will shake, like they will move around, right? If let's say if there is no path, so what will happen? Then they will like push around, right? So these electrons will push all the electrons sitting around these electrons, and the next one will actually starts to shake, right? And then will push the other one in the next. And this is way that will gradually the electrons in the right side also starts to move, and you will feel the heat in this side. Right. So this means that when we apply heat, then those carriers get some extra energy and move up and will go to the conduction band and will conduct. Conduct means actually moving around. Is free to move. So what happened? So this when I say here. Because of this band diagram, right? Because the silicon is only one piece of silicon, so it will be the same. But when you say when I mentioned here, let's say this one is I say aluminum, gallium arsenide, right? So what will happen? Aluminum arsenide, gallium arsenide. This you see that there are three different materials are actually combining and forming one. So they are these things are not same. Let's say, for example, if we consider this is for gallium. Any question? No. Okay. Let's say we can consider this side. Let's say this is for gallium, right? And use a different color. And let's say this is this one, and let's say this one, and this one. Let's say this is for arsenide, and let's say this is for aluminum. Let's say for aluminum, maybe this one, and let's say here. Right? This is a three level, right? So understand this. This is three things, three level of energy. Let's say for example, aluminum has energy level like this. When the carrier living here has no energy, when the carrier living here have enough energy. Right? So if we have like that, right? You see now these are three different material, and when you making together, right? When you combine together, and they will form a one atom, then there will be some kind of because since they are making one, so there'll be energy band like this. You see, this one is open. Okay, so I can put it here straight. Right? You see the diagram here. When they are combining, their diagram will be their energy diagram will be looks like this. Right? So this is the important component. Right? This is the conduction band, and some of the electron carriers are sitting here with the what is called with a hill. No, what's called bottom hill. We can say in the bottom hill. So this is the place those vacuum is formed, right? Because of the hill, you see the conduction. There are some electrons here, and electrons will be coming here, and so they will form a vacuum place, and so there is we call it not vacuum. The name is what is called two two-dimensional electron, actually. Two-dimensional electron. Right? What do you mean by two-dimensional electron? Do you understand? Two-dimensional electron gas, right? Not degree, 2 degree, not 2 degree, right? So what is happening? Let's say when you put a huge number of electrons. I'm always talking about electrons, right? Actually, it will be the carrier. Let's say if we put some electrons here and electrons here, right? So, and if we measure this, what will be that? There should be 3-dimensional, right? Do you understand? This electron is a what is called is a atom, right? When you bring an electron and put it several let's say the 9 electrons together, so they will form they will have a W, L, and H, right? So it should be 3D, right? All kinds of things, right? When whatever the materials or what kind of, it doesn't matter what kind of device, what kind of atoms or what kind of materials. When you bring a lot and put it together, it will be always 3D. It must be have W, right? Width, length, and height. But in here, the interesting is here, they will form a very thin, like a very thin layer of electron. Right? You understand? This is a very thin layer of, right? Very thin layer of electrons means the thickness of the paper is almost zero. Right? Maybe only one electron. The thickness is only one electron, right? So there will be no height. Only this. Let's say this is length, and this will be width. There will be only width and height. Width and what is called length and width, right? There will be length and width, and the height. This thickness is very slim, so we can consider that is zero. So that then it will be considered as a two-dimensional electron gas, right? And when you have a two-dimensional electron gas, so it will be forming like a cloud, like a thin pieces of paper, and there will be all electrons, and all electrons will be moving here, right? So there will be no collision. That's the way it considers that there will be no collision inside, right? So that is actually approximately things, and if we want to more understanding, then we have to go to the higher level, right? And we'll design exactly how we are making those kind of transistors, right? So this is the basic understanding, right? But we'll go back to our diodes, right? So what happened to the diode here? And okay, first thing we already know that when you apply this is there is a name, right? It's called forward bias, right? This is called forward bias. What is forward bias? Anybody has any answer? Or what is how many kinds of biases are there for diode? Have you studied?
Sir, two types,
Yeah,
forward and reverse.
reverse. So why it is called forward? Any idea?
So because the holes are attracted to the electrons, free electrons of n.
Yeah, the holes, these holes will be attracted by electrons, right? And these holes, and this positive, the positive voltage actually the pushing. Let's say this one is attracted by this one, and this, let's say this one is attracted by this one, and this one is pushing by this one, right? So that means there will be no, not this one. This pluses will be moving this way, and the electrons will be moving this way, right? Right? This is the way. Right? So when this one moving, so that means the current will on. The electrons will flow, and electrons here. The electrons will moving from left to right, and the current moving from left to right. Right? This is the way, right? We also know that when you apply some positive voltage, the current will go this way, right? So this is the right direction, and the direction of the current is right. That's why we call it forward. Right? It's going forward. When we are moving forward, this is the right direction. And going back is not the right direction, right? Going back is opposite direction. That's called reverse. But this one is a forward direction, means the right direction. So in this is the current is going in the right direction. From current is going from here, you see positive to negative, right? That is the direction of the current, and the electrons will moving from negative to positive. Yeah, that is the right direction. Negative is supposed to be moving from negative to positive. Yes, you see, negative is going to positive, and positive going to the negative.
So can we also say that P side are the P side is connected to the positive terminal and the N side is connected to the negative terminal?
Yes, yeah, that's right. So that's, yeah. So P side is connected to positive, N side connected. That's the way that is. It was connected. That's why it's doing the right way. Right? The current is flowing in the right direction. Right?
Yeah.
And also, what happened to this boundary line? I put a line here. What will happen? This one. When you apply the positive, this will be remain here. What happened? When you apply positive voltage and up 0.7 or a little bit more, what will happen to this? The virtual line, there will be nothing, there will be disappear. This will be disappeared. When you have forward bias, there will be nothing. This is there will be nothing. So no boundary line. Right? So what will happen? All the positive will moving this way, positive moving this way, and negative moving this way. So then there will be transport. Right? Right? Then the carriers will try to move from one side to the other side, right? And there will be no shortage of carriers, because let's say this carrier, this positive is moving from here left side to the right side and mixing, right, and combining with these electrons, and will turn zero, right? Right? Recombine. This is positive and this is negative. Let's say these two are connect, combining and recombining and becoming zero. But what will happen? But there will be no shortage of holes here. More holes are coming from here, right? There will never be shortage. And also in this side, if these electrons are, if this electron moves here and recombine, then become zero. Then more electrons will be coming from here, right? So that means this is the voltage. This is a source, is a universal source. So there will be no shortage of electrons and holes from here. So electrons coming from this side, holes coming from here, and will continue all the time, right? So that is the positive. No, that is the forward bias. And if you make a graph, so what will happen? Initially around 0.7, right? After 0.7 volt, there is no current, and then after that, and the current will start to increase, right? And that's the way. And this is a curve, IV characteristic curves like this. Right? Any question about this? Forward bias is so easy, but the problem is the reverse bias. We'll see the reverse bias now. Right? What will happen to the reverse bias? So let's say we are drawing another piece of diode, and this is a P, N, and the N type, there are 6 electrons and 2 holes, and there are 6 holes in this side and 2 electrons. And now in case of reverse bias, what we have to do? We have to put the opposite polarity, right? We have to put a positive in this side and negative in this side, right? So what will happen? So
So
what is
virtual
the
barrierটা থাকবে তখন।
থাকবে?
জি।
Yeah. What is the virtual barrier? Why is that? Okay, if we don't put any voltage, so what will happen to this barrier? If we do not apply any voltage, is there any barrier here or no?
So I think there should be a barrier.
Yes, that's good. Yeah, right answer. Thank you. And why is that?
So কারণ
How do you-
inside there's still like holes তো still আছে. So when P side holes গুলা will still be kind of repelled. So barrier still exists.
Yeah, good. You're close, very close. And what is the name of this virtual barrier? Remember?
না স্যার এটা মনে নেই।
Depletion.
It's a depletion region.
Yeah. Depletion region. So I'm just drawing it a little bit bigger so we can show what is actually there. Right? Okay, maybe we can make it a little bit more bigger so we can show more stuff. Okay, let's say initially the virtual barrier was like this, and this is the middle point, right? Let's say consider this a middle point. So what was in this side, left side, there was hole, right? There was a hole, and because this is a p-type, and in this side there was electron. Let's say I put 4 electrons in the right side and 4 holes in the left side. This was the original, right? And then, right? When it was a 2-piece, let's say this was completely 2 pieces, right? Let's say this is 1 piece and this is 1 piece, and we are not bringing close to each other. Let's say that this is a 2-piece, but we are not connecting. We are still gap, right? We are not using. We are not connecting. So when we connect, there's a gap, so that means this is one side and the side. So this will be looks like this. There is some holes in the left side and there are more electrons in the right side. But when you bring it here, right, connecting each other, so what will happen? When you connect, right, 2 pieces during fabrication, right? When you bring 2 pieces, so what will happen? These holes and these electrons, because they are very close to each other, right? They are side by side. So they will recombine. Understand? They will recombine, and so that means when they will recombine, then they will be neutralized, right? But what will happen? When they recombine, they left some ion, the opposite ion. Right? Because in this atom, when the positive carrier, let's say this is an ion, let's say this is the whole thing, whole atom, and when whole atom has a positive and negative, right? This is a neutral atom. Neutral atom has hole and electron, but when these holes goes away, so what it left? It leaves the electrons here, right? That is called ion, right? When the electron moves, right, moves away, then it it leaves an electron on that spot, right? In that, let's say if we consider this whole thing is an atom. If we consider the whole thing is an atom and this another is atom, let's say these are two atoms, and both were neutral before. And now when we brought these two atoms close to each other, so in the outer shell, right? You know that there are in physics or in intermediate, right, or high school, you studied that in atom, and inside there is a what's called neutron and what's called proton, right? And there is some outer shell, there is some electrons, right? So when what happened? And what is this one? What is negative means and positive means? Negative means this outer shell has extra electrons. Let's say extra electrons are there. And when you say the holes, the positive, that means there are some shortage of electrons in the outer shell. And there is shortage of electrons. Then it turns into positive. So now in here, let's say let's consider this electron side, because it's easy to understand from the atom, because we know this electrons are actually sitting outside, so it is easy to understand. Let's say the electron in here, and let's say that this atom, in the right side atom, this is a negative ion, right? Negative atom. So negative atom means there are more electrons in the outer shell. Right? Now, if this extra electrons goes away, right? If it goes away, so what happened to this one? This one turns into positive. Understand this? Do you understand?
Yes, sir.
Yeah. When some atom lost some of the electrons from its outer shell, then the whole things become positive, because we know that number of electrons and number of protons are equal when it is neutral. But when some lost some electrons, then the number of protons becomes more than the electrons and becomes positive ion. Right? So that things happen here. So some electrons will leave from here in the right side and goes here. Right? So then in the right side, what will happen? I'm showing only one. I'm showing by the blue color. Let's say from right side there was an electron, and that electrons, right, left this place. So then what happened? The positive ion will be leaving there, and I'm using the circle. And because this is an ion, not the free electron, not the free carrier, this is different than this one. These are the free holes, because these holes have enough energy to move, but this one has no energy to move. Right? This is called ion. I'm using circle. And what will happen? This extra electron went to the left side and added with this one, and then that one will be turned into negative ion. This one turns into negative ion, and that one also has no enough energy to move.
Sir, can you repeat again?
Okay, try to understand the right one first, because this one is hard to understand.
Sir, I
Right.
understand.
I'm showing, okay, I'll show you. I'm using another figure in here. Let's say let's say positive, not a circle. This one positive and this one negative, right? And we're considering this is an atom, right? From this atom, right? This is a negative atom. And I'm showing here the negative atom means in here. Try to understand this one. This is proton and neutrons are in the center, and outside, let's say outside, consider that let's say consider this a five proton, and there are 5 electrons. Let's say here, right? Just for example, 5 electrons, and let's say this one is this. Okay, no, this, let's say this one. But when it's a 5 and this one 5, this is neutral. But let's say add one more extra electron here. Let's say one more extra electrons in this side. So now what will happen here? This atom is negative, right? You understand this?
Yes, sir.
Because this one is electron, and proton is here, electron and extra electron we added in order to make this whole thing negative, like this one, showing here. Inside the silicon, this is this one. This whole thing is representing by this, and because one extra electron is more, and this atom is here. So now, if we take, let's say, if we take these 3 electrons from here, from this atom, and put it here, so what will happen to this atom?
It will become positive.
It will become positive, right? So it will become positive, and it cannot move because it has lost lots of energy, right? Energy lost, it will turn into an ion, and will be sitting in the bottom of the valency band. I have shown the band diagram, conduction band, Fermi level, and the valency band. It will sitting on the bottom, and it cannot move. Right? Move, but it needs more energy to move. Right? In order to move this one, it will turn. It needs more energy. So that's why we call it ion. It's a positive ion, not anymore atom. Right? Because it lost lots of the energy. What's called energy components. Right? The component which had energy has lost. For example, a human being, let's say, lost 2 of its legs. So what will happen? It cannot move anymore. Understand? Understand this one? The same thing. So now this is the opposite to the other side. So when it lost some of those electrons, some of this energy, right? But we are not explaining the same way in the left side. Same way we'll explain. Let's say this is another one, another atom. Right? Another atom has a positive, right? This side is a positive, and from here, some of those positive actually went out. Some of those positive, right, left left this atom, and you see some of the electrons came from here, and some holes came from here, and they recombine. They right, when they mix together, they turn to 0. Right? It turns into 0. So then what will happen here? So if some of the holes left this place, so this place will turn into negative, right? It was positive, so it will be opposite to this one. It will turn into negative, and it's called ion. This will be turned into an ion, negative ion, right? It's opposite to this side. So this side is a little bit hard to understand because the holes actually nothing, right? So this is a complicated a little bit. So, but try to understand this one, right? I think it was easier to understand. So it will be opposite effect in the opposite side. Understand now?
Yes, sir.
So now you see, now in this side will be negative ion, and in this right side will be positive ion. So what will happen? All of this turns into,
it will attract.
it will positive. You see here, in the right side there will be positive ion, and the left side, all positive turns into negative ion here. So this is called depletion region, and they are not moving. Right? So you see, they have no enough energy to move. Right? This is the depletion region. We do not apply any more any voltage. So this is the inside. This is N. This is P, and in between there is a barrier. Now you see what happened to this. This one actually making a barrier for the other. This one acts like a wall, right? Acts like a wall, and it will try to force those free holes and electrons move away. You see here whatever. Okay, let's consider here. You see, this is an ion, right? Negative, and this ion, let's say in this, this is free electrons, right? This one is a free electrons. What these electrons want to go? Where this electron want to go? This electron want to go to this side, right? And these holes want to go this side and want to be neutralized with this, right? this one and this one want to recombine each other. But what will happen here? You see, when this one want to go the left side, then this negative ion will make a repulsive force between this one and this one. Will make a repulsive force, right? And this positive ion and this one will make another repulsive, right? So that means these two actually move this one away from here, and this one will actually leave, right? Move each other away. Understand?
Yes, sir.
So this is the way it stops the movement of the other free electrons and holes from one side to the other side. I'm showing only one layer, but there'll be more layer, right? Of course. And there'll be
Sir,
multiple.
but if we provide a voltage, then it will move diode.
Yes, exactly. So this is the initially it will looks like that. And now when we apply a forward bias, whatever we have just applied before, forward, whatever. So that means you are applying more force here, right? When you apply more force, then they will break down this small wall, right? They will break down and will cross, right? If you have like a small wall, so you can just break, right? You can just kick, like if a small wall is made out of the hardboard, right? It can easily break down, right? But but you need of course some energy. But if you don't have energy, you cannot break. Right? So you have to apply some energy. And what is there? How much energy you need? 0.7, and that is a threshold voltage, VT. Right? So you need a 0.7 volt to break this wall. Right? So that's a 0.7 volt. I show you. We show here. So before 0.7 volt, right? Right? In here there is no current. Right? Once you apply, when you go like a 0.2, 0.3, 0.7, 0.5, 0.6, there is no current. That means the wall is not broken yet. Right? When you apply 0.7, this wall will be broken, and then the holes will go this way, and the electrons will go that way, and the current will start to flow from here. Right? No problem. But what happened now? Look at this other way, reverse. We wanted to study the reverse bias. What will happen here? Now you see, is it giving the energy? Is it giving? Is it positive? Is it positive giving this electron more energy to cross this, or it is going to? So, is this positive? This is the positive terminal is connecting to this terminal. That means this positive.
Yes, sir. Telling they are attracting.
They will attract in each other. So these electrons will not go that way. This will be attracted this way, right?
Yes, sir.
That means it will actually pushing or is pulling backward, right? So this one is actually pulling back, and this one also, and this one will be pulling backward by using this negative ion. And this is negative voltage, negative terminal. Right? So this one will be pushing backward. This one also will be pushing backward. So what will happen then? This depletion region will actually increase. Right? You see, this negative is moving away, this negative moving away. So this one will be turns in this one, positive ion, and this one, on these holes will be moving away. So this one will be negative ion, negative ion, negative ion. So now you see what happened to the depletion region? Before it was like this much, and now this much is bigger. Right?
So the conduction কি হবে তখন? Like will
Conduction
current-
হবে না. No, there is no conduction.
Okay.
You see, the depletion region is bigger. Depletion region to বেড়ে যাবে না, reverse bias current যায়.
No.
There is no current. Right?
And
There
it
will no
won't matter how much voltage we give, 0.7 or যাই হোক, it doesn't matter.
No, it is not 0.7. It's the negative voltage. So that means you are applying a voltage in this way, right? -1, -2, -3, right? You see, this is voltage is negative, and opposite. You are applying opposite voltage. No, there will be no current. There will be no current. The current is zero.
Okay, got it.
Yeah, when you reverse bias, there will be no current. But there is a but there, right? What will happen when you increase? When you increase this voltage very much, right? Let's say if we apply 30 minus 30 volt, right? Normally, how much is the operating voltage for the diode? Normally, we use normally 5 volt, right? Right? 0 to 5 volt. Let's say 0, 1, 2, 3, 4, 5 volt, right? 4, 3, 2, right? Normally, electronic device normally operates at 0 to 5 volt, or maybe in some cases is at 12 volt. But when you increase this reverse bias, right? When you because the polarity is different, it's opposite, so that means we consider opposite means we are considering the minus voltage. So when we increase this opposite voltage and gradually increase and going too much, right? So what will happen? So you see this gradually increasing, right? Increasing, and then will be full, right? It's full হয়ে যাবে না?
But depletion regionটা বড় হতে হতে it'll cover up the whole transistor.
Yeah, whole transistor, and then what will happen? Then what will happen? Whole transistorটা cover হয়ে গেল, তারপর কি হবে? তারপরেও তুমি you are applying more, still you are applying, right? And what is this? This when increasing voltage, that means you are applying lots of energy, right? You are applying energy to the what? The carriers. কি হবে এটা? After the whole thing is full, then it will be broken. Then the whole things will be disappeared and will be broken, right? And then the current will start to flow. The whole thing will be broken, and the current, it will be right a short circuit, and the current will start to flow the opposite direction, right? So in here, after a very high voltage, then the current will start here, and the current will be starting opposite direction here, and straight very large current will flow, not gradually increasing. It will be right. Let's consider minus 30 volt, and it will be going this way, and this will broken. It will you cannot use this one anymore.
So permanently broken হবে.
Permanently broken, yes.
Okay.
And broken hole কি হবে? It will be looks like a short circuit, and then it will be growing. The current will be bigger, too big. Right? That's you studied Zener diode, I think, right? You studied Zener diode.
Yes, sir.
Yeah, the Zener diode is a different, right? A different properties that can be that can be recovered. The Zener diode is the construction is a different material, and that can recover from the breakdown point. Zener diode শুধুমাত্র এই যে এই পয়েন্টে হাই কারেন্ট ফ্লো করার পরে আবার ব্যাক করে আবার নরমালে অপারেট করে যায়. Other than that, all the other diodes will be broken permanently, will never recover. Right? That is the basic principle. So when we study our main topics, we need these two things, right? This forward bias and the reverse bias of the diode. So if you understand this diode clearly, then the transistor is nothing. Transistor is just two diodes, right? You can see PNP or NPN, whatever. If you understand one, then will be other one is simple. So now this one has a PN junction, and this one has a PN junction too, but it's opposite way, right? So there is a depletion region, and there is another depletion region. So now how those transistor works? There will be since there is a two diodes, so we need a two voltage, right? So the one voltage is here, and another voltage between here and here, right? Now it depends how do you do that, what kind of voltage you do. So now instead of two different lines, what do we do? We use a single line, right? We just connect this point, right? This is the way. Now, how do you operate this junction? The principle is there is two diodes. Let's say the diode 1, diode 2, right? So one diode must be forward bias, and another diode will be reverse bias, right? Remember that one of the diode will be operating in reverse, and another one will be in forward. So now, which one you want to do? You can do whatever you like. You have no problems. If you want to, normally we use those the left one the forward and right one reverse, but you can do the other way because these are same, right? Let's say if we want to make this one forward bias, how can we do that? What will be the polarity of this voltage? One side is positive, which side will be positive? If we want to make this junction forward, this diode forward, which side will be positive in this voltage?
So right one.
Right?
Yes,
Here,
sir.
if we
Yep.
put it here positive and here negative, so what will happen here? You see, the N type is positive and P type negative. Is it a forward bias?
No, sir.
Oh no,
Opposite.
এটা reverse. এটা
This is
opposite.
reverse. This is reverse. You have to put it this side positive, this side negative. Then this one will be this diode will be forward bias. So now this will put it here. Now this. So this one is forward bias, and out of this one must be reverse bias. So that means reverse bias means, okay, we can connect in here, so it will be looks better. So this one, so then in order to make it reverse bias, the P side will be connected to negative, and N side will be connected to
Positive.
positive. So now so this N side will be positive and the P side is negative. Now it's done. Right? This is forward bias. You see this junction. This diode is a P diode. P is connected to negative, and N is connected to positive. This is reverse bias, and this one is positive is P, and N is negative. So now this is open, and this one, if we want to make this one, we can do the same way. Here, there is a junction here. So you want to make this one positive. Let's say left side. Normally we do that. Left side positive. No, forward. Left side forward. If you want to make left side forward, so what do you have to do? In this side will be negative, and this side will be positive, and in here. This is positive, negative. So now it's forward bias, and this will be reverse bias. So the N side will be positive, and P side will be negative. Negative, positive. Now that's done. And all the operations will be exactly the same as diode, because these are two diodes, two voltage will be operating. Okay? Now look at the current. So, we already mentioned that the reverse bias current is almost zero, right? I told it is zero, but actually there is no zero. Very negligible current actually flowing because of the reverse bias and because of the leakage. Some very little. But in here, what happened? But the forward bias, there are lots of current, right? So when this one is a forward bias here, so this one will disappear, and the current starts to flow here, right? So this is the current, right? Current starts to flow. But what happened to this one? Reverse bias?
So
This one is reverse bias, right? But there will be almost no current. But you see, here is a positive voltage here. So positive voltage will actually giving this little amount of current here, right? So now look at this terminal, this branch. One current is going downward, and one current is going upward, right? And this is actually the base, right? Remember the base collector emitter, right? You already studied, right? The base. This, right? This is the base, and what is this one? What is this one? Is a PNP. So it'll be P here, N here, and P here, right? This and this one. If you want to draw this one, so this N is the first one, is N, base is P, and N there is here, right? This way. Right? So this is the symbol. Oh, and the direction is here. The current always goes from P to N, so it will be here, and the current going from P to N, so it will be in the other way, right? So this is the direction, and that is a symbol, and this is the way. And you see the look at the base, and this one also is here. This is the positive, the forward bias here. The current will flow this way, and this other one, right, is going upward. And then the reverse bias here, and then a little amount of current will flow this way. You see, this is a base, and this is a collector emitter. And now see, look at the base. Base in base, there are two currents. One is going upward, here is going upward and going downward. Here also going downward, going upward, right? So if it is upward and downward, so then the resulting current will be the subtraction of the one to from the bigger one to the smaller one, right? And that's why the base current is very, very small. Right? Base current is very little compared to the other current, right? The base current, remember, the base current is very small. Right? I think so. This is this one is enough.
So the resulting current will be small.
Yeah, the base current, because you see the base.
Yes, sir.
There are two currents going through the base. One is going opposite to the other current. That's
So
why the
if we
base current.
subtract these two, then we'll get the base current.
Yeah, subtraction of those two currents in both cases. Right? The same thing for others. So that's why the base current is bigger. No, very small. And I think you will do the experiment very soon, maybe next class. You will see that the base current is very, very small because of this one. Right? Because the two currents flowing in opposite to the other one. Right? And whose current is bigger? The forward current, right? And if you look at here, the forward current, where is the forward? Yeah. So this current is the bigger one. And this is the bigger current. And what is the bigger current? Emitter. Right? Emitter current is the bigger current, right? You know the equation. I is equal to, what is that? IC plus IB, right? Base current plus collector current. This is a collector here. And in this case, what is the reverse one? Yeah, this one, this current will be flowing here. That is IE, and this side is IC. And also another formula, we had alpha equal to how much? IC divided by IE. How much is that? Remember? Approximately. Because I already mentioned that a base current is very, very small, right? If the base current is very, very small, and base current is very, very small, sometimes the IC is close to IE. And if this IC and IE is close, so then this will be close to 1. But normally it's 0.98, around 0.9 or something, right? 0.98. But another terms you need to remember, right? We need it.
Sir,
That
I
is
have a class at 5.
what is it?
Sir, I have a class at 5, sir.
Oh, 5. Oh, okay. Oh, 5 o'clock already. Okay, just one more. Okay, you can leave beta. Beta is equal to IB by IC. Remember that? The beta. This one is bigger because I did a mistake. IC by IB. IC by IB. So IC is bigger, but IB is so small, that's why beta is approximately equal to 50 and 10 to 100, something like that. And beta is bigger, but alpha is small. Alpha is IC and IB almost the same. Okay, thank you. So those who are who have a class, so you can leave. And other, if you have any questions for today's class, okay, let's see. Let's close first. We stop the recording.
Sir, for our attendance.
Oh, I forgot the attendance, right? Oh, I forgot the
স্যার আমাদের কি কোনো স্লাইড দিবেন?